Take a moment to listen to the silence. In that silence, think about one of the most fundamental and inescapable laws of the universe. A law that governs everything, from the dying of the stars to the hot cup of coffee on your table. It is the second law of thermodynamics. It states, simply, that everything in the universe tends to move from order to disorder. An intricately built sandcastle will be broken down by the wind and the waves into a shapeless pile of sand. A drop of ink in water will spread out until it is completely dissolved, never gathering itself back together. Energy always tends to disperse. Order always tends to decay. This is the irreversible arrow of time. But if that is so, then why do you exist? Look at your own hand, an astonishingly complex structure of trillions of cells, each cell a miniature city, all working in perfect harmony. Life, in all its forms, is the pinnacle of order, a symphony of exquisitely organized complexity. It seems to go against the most basic law of the cosmos. It is an exception, a defiance. So, could it be that life is the universe's most beautiful and extraordinary mistake? Welcome back to Science for Sleep. If this journey into the deepest paradox of existence sparks your curiosity, a gentle tap of the like and subscribe buttons will help us continue these voyages together. And as always, I would love to know where you are listening from in the world. Please feel free to leave a greeting in the comments. Tonight, we will begin an investigation, not to break the law, but to understand it. This is the story of life's quiet rebellion against a chaotic destiny. A story of how temporary flames of order can burn so brilliantly in the endless night of the universe. Let us begin. To understand life's great rebellion, we must first understand the nature of the tyrant it is rebelling against. This tyrant is not a conscious entity, not a malevolent force. It is a quiet, patient, and absolutely fundamental law of the universe. It is the second law of thermodynamics, and its central character is a concept known as entropy. The word itself can sound intimidating, a piece of scientific jargon best left to physicists and their chalkboards. But at its heart, the idea of entropy is beautifully simple and deeply intuitive. It is, in essence, a measure of disorder, of randomness, of chaos. A system with low entropy is one that is highly ordered, structured, and predictable. A system with high entropy is disordered, random, and chaotic. Let us use a gentle, familiar analogy. Imagine a brand new deck of cards, just opened. The cards are in a state of perfect order, ace through king, sorted by suit. This is a state of incredibly low entropy. There is only one specific way for the cards to be arranged in this perfect sequence. Now, imagine you take that deck and simply toss it into the air, letting the cards scatter across the floor. They will land in a random, jumbled mess. This is a state of high entropy. And here is the crucial insight. There is only one way for the cards to be in perfect order, but there are a virtually infinite number of ways for them to be in a disordered state. It is for this reason, a simple matter of probability, that the universe always tends towards disorder. It is not because chaos is an active force. It is because chaos is, by an overwhelming margin, the most likely outcome. Entropy is the reason a hot cup of coffee will always cool down to room temperature. The heat, which is the ordered, concentrated energy of fast-moving molecules in the coffee, will inevitably disperse into the cooler, more disordered air of the room. The heat never spontaneously gathers from the room and flows back into the cup to make it hot again. It is the reason a carefully built sandcastle will always, given enough time, crumble back into a random pile of sand under the patient influence of the wind and the waves. The universe is always moving from the unlikely state of order to the overwhelmingly likely state of disorder. This relentless, one-way journey from order to chaos is what gives time itself its arrow. We can remember the past, but not the future, because the past is a more ordered, lower entropy state. The future is a more disordered, higher probability state. The feeling of time flowing forward is, in a very real sense, our direct, conscious perception of this fundamental law of probability unfolding all around us. It is the universe's quiet, irreversible sigh as it settles, moment by moment, into a more chaotic, more probable version of itself. This is the God of chaos. Not a deity of malice, but a simple, unshakable law of statistics. A gentle but constant pressure that pushes everything, always, towards the quiet equilibrium of disorder. If we follow this irreversible arrow of entropy to its ultimate conclusion, if we ride the great, slow river of time to its final, silent sea, what do we find? What is the ultimate fate of a universe that must always move towards greater disorder? Physicists have a name for this final state, a name that is both poetic and chilling. They call it the heat death of the universe. Let us now take a journey in our minds, a journey not through space, but through an almost unimaginable expanse of time, to witness the long, slow, and peaceful end of everything. We travel forward, past the lifetime of our sun, past the age of the earth. We journey trillions upon trillions of years into the future, into an era that physicists call the degenerate era. By now, the great age of stars is over. All the suns that once lit up the galaxies have exhausted their nuclear fuel. The last red dwarf, the longest-lived of all stars, has finally flickered and died, becoming a cold, dark, black dwarf. The universe is no longer a place of brilliant, shining galaxies. It is a vast, cold, and profoundly dark expanse, populated only by the dead relics of stars, black dwarfs, cold neutron stars, and the silent, patient black holes. The galaxies themselves have begun to dissolve. The relentless expansion of the universe, driven by dark energy, continues to stretch the fabric of space-time, pulling everything further and further apart. The great clusters of galaxies have long since drifted away from each other, vanishing beyond the cosmic horizon, their light no longer able to reach us. Even the remaining stars within our own local group are slowly being scattered, their gravitational bonds weakening over eons. The universe is becoming a thin, cold soup of stellar corpses. But even this is not the end. Over a timescale so vast it defies all human language, even these dead stars will eventually decay. Protons themselves, the very building blocks of matter, may be unstable and could, over an almost infinite amount of time, decay into lighter particles and radiation. The great, dark cinders of stars will slowly evaporate into nothingness. The only things that remain are the black holes. This ushers in the black hole era. For an even longer period, the universe is a realm of almost total emptiness, dominated only by these gravitational ghosts. But even black holes are not eternal. As Stephen Hawking discovered, they too slowly lose mass over time through a process of quantum evaporation known as Hawking radiation. It is an incredibly slow process. A solar mass black hole would take 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies would take far, far longer. But eventually, after an age that makes the current age of the universe seem like a fleeting instant, the last and largest black hole will radiate away its final particle of energy in a final, faint flash of light. And then, the universe enters its final state, the dark era. It is a state of maximum entropy, of perfect and final equilibrium. It is a vast, cold, and near-perfect vacuum, filled only with a thin, uniform sea of low-energy photons and other elementary particles, all drifting aimlessly and endlessly through an ever-expanding darkness. There are no structures, there are no temperature differences, there is no flow of energy, there is no change. Time itself, which is defined by the arrow of entropy, loses its meaning. This is the heat death. It is the ultimate fate of the cosmos, the final, quiet victory of the god of chaos. It is a state of perfect peace and perfect emptiness, and it is from the very opposite of this state, from a moment of perfect and improbable order, that our story of life must begin. Having journeyed to the cold, quiet end of time, to the final, peaceful equilibrium of the heat death, We must now travel back. We rewind the great cosmic clock, past the age of stars and galaxies, all the way back to a time just after the birth of our own solar system, around 4.5 billion years ago. We are here to visit the cradle of life, to see the stage upon which our story would eventually unfold. But this cradle was not a gentle or peaceful place. The primordial Earth, in its infancy, was a world of pure chaos, a perfect embodiment of the universe's love for disorder. This was the Hadean Aeon, a name taken from Hades, the ancient Greek underworld, and it was a name well earned. Imagine a world not of blue oceans and green continents, but of fire and rock. The young Earth was a molten sphere, a global ocean of magma heated by the immense energy of its own formation and the constant decay of radioactive elements in its core. Its surface was a churning, glowing sea of liquid rock, with no solid ground to stand on. The sky above was a thick, oppressive blanket of toxic gases, a primordial atmosphere with almost no free oxygen. It was a choking mixture of carbon dioxide, nitrogen, water vapor, and poisonous compounds like methane and ammonia, all vented from the planet's volcanic interior. The sun, younger and fainter than it is today, would have been barely visible through this thick, reddish-brown smog. And from this hostile sky, there was no gentle rain. Instead, there was a constant, violent bombardment. The young solar system was still a messy construction site, filled with the leftover debris of planetary formation. For hundreds of millions of years, the Earth was pummeled by a relentless rain of asteroids and comets, some as large as mountains. Each impact was an event of unimaginable violence, releasing the energy of thousands of nuclear weapons, vaporizing rock, and keeping the surface in a perpetually molten state. This was a world being forged in fire and violence, a chaotic and high-entropy environment, where the formation of any delicate, ordered structure seemed utterly impossible. But slowly, over an immense stretch of time, the planet began to cool. The heaviest elements, like iron and nickel, sank to the center to form the core. A thin, primitive crust of solid rock began to form on the surface, like a fragile skin on a cooling bowl of soup, only to be constantly shattered and remelted by the next great impact. As the cooling continued, the water vapor in the thick atmosphere began to condense, and it began to rain. This was not a gentle, life-giving rain. It was a torrential, acidic downpour that lasted for millions of years, a great deluge that slowly filled the low-lying basins of the new crust, forming the first hot, primordial oceans. This was the world, the chaotic cradle, in which the first rebellion against entropy had to begin. It was a world that, by all rights, should have simply continued on its path of cooling and settling into a quiet, sterile equilibrium. It was a perfect stage for chaos, a place where the second law of thermodynamics was in its full and glorious power. And yet, it was here, in this most unlikely of places, in this hot, violent, and chemically chaotic soup, that something extraordinary, something that seemed to defy all the odds, was about to happen. The first quiet whisper of order was about to emerge. The paradox is now laid before us, a profound and beautiful contradiction. On one hand, we have the second law of thermodynamics, the universe's most fundamental and unshakable rule, which states that everything must inevitably decay into a state of greater disorder, of higher entropy. On the other hand, we have life itself, a phenomenon of breathtaking order and complexity, which seems to defy this law at every turn. It is a rebellion, an island of intricate structure in a vast cosmic ocean of chaos. How can this be? How can life build its magnificent ordered castles on the shores of a universe that is constantly trying to wash them away? The answer is not that life performs a miracle, or that it breaks this fundamental law of physics. The truth is far more elegant. Life does not break the law, it has found a loophole. The second law of thermodynamics, in its strictest sense, applies only to what physicists call a closed system. A closed system is one that is completely isolated from its surroundings. It cannot exchange energy or matter with the outside world. The universe as a whole is the ultimate closed system. It has no outside to interact with. And so, its total entropy must always increase. Its story must always be a one-way journey towards the final equilibrium of the heat death. But a living organism, a single cell, a tree, is not a closed system. It is a profoundly and beautifully open system. It is in constant, intimate conversation with its environment. You breathe in the ordered molecules of oxygen from the air and exhale the more disordered molecules of carbon dioxide. You consume the highly ordered chemical energy stored in food and release the disordered, low-grade energy of heat back into your surroundings. Life is a process of constant exchange, a river of energy and matter that flows through us, not a sealed and isolated box. And it is this openness that provides the loophole. An open system can decrease its own internal entropy. It can build and maintain its own incredible order, but only by doing one crucial thing. It must increase the entropy of its surroundings by an even greater amount. The total entropy of the combined system, the living organism, plus its environment, still increases, and so the second law of thermodynamics remains perfectly satisfied. Let us use a simple, gentle analogy. Think of a whirlpool or a vortex forming in a river. It is a beautiful, highly ordered, and stable structure. It is a pocket of low entropy, but it can only exist because it is part of a much larger open system, the flowing river. The vortex maintains its ordered shape by taking in the energy of the flowing water and, in the process, creates a great deal of disordered turbulence and friction, high entropy, in the water all around it. The vortex is an island of order, paid for by exporting a greater amount of chaos to its surroundings. Life is this vortex. It is a temporary, beautiful, and self-sustaining pattern of order that has learned to harness a flow of energy. It is not a violation of the universe's rules. It is the most clever and beautiful exploitation of them. It is a quiet rebellion, fought not with defiance, but with a deep and innate understanding of the very laws it seems to oppose. Life does not fight the current of entropy. It has learned to surf upon its wave. But for this to work, it needs a constant source of energy to draw from, a great cosmic river to power its beautiful, ordered vortex. And that brings us to the next chapter of our story, the great external engine that has paid the energetic price for every living thing that has ever existed on our planet. Life, then, is a beautiful vortex of order, a self-sustaining pattern that has found a clever loophole in the universe's most fundamental law. It can build its intricate structures, it can maintain its delicate chemical balance, and it can fight off the relentless tide of decay, all by being an open system. It creates a pocket of low entropy, a local island of order, by exporting a greater amount of chaos and disorder to its surroundings. But this cosmic accounting trick requires a constant source of payment. To create order here, you must draw energy from somewhere else. The great, quiet engine of life needs a fuel source. And for every living thing on our planet, from the deepest microbe to the tallest tree, the ultimate source of that fuel is a great thermonuclear furnace, 150 million kilometers away. It is our sun. The sun is the great external engine that has paid the energetic price for life's rebellion against entropy. It is the constant, reliable flow of energy from the sun to the earth that allows the beautiful vortex of life to keep spinning. But it is not just any energy. The specific quality of the sun's energy is what makes life possible. To understand this, we must understand that not all energy is created equal in the eyes of entropy. There is useful, ordered, low entropy energy, and there is useless, disordered, high entropy energy. Let us use a gentle analogy. Imagine you have two sources of heat in a cold room. The first is a single, intensely hot needle, heated to 1,000 degrees. The second is the entire room full of air, warmed to just slightly above freezing. Both systems might contain the same total amount of thermal energy, but the quality is vastly different. The hot needle, represents a state of low entropy. Its energy is concentrated, ordered, and highly useful. You could use it to boil a drop of water or power a tiny steam engine. The warm air, on the other hand, represents a state of high entropy. Its energy is diffuse, disordered, and spread out. You cannot use it to do any useful work. The sun provides our planet with low entropy energy. It is an incredibly hot point source in a very cold sky. It bombards the Earth with a steady stream of highly energetic, highly ordered photons of visible light. This is the cosmic equivalent of the hot needle. This is useful, high-quality energy. Life, in its profound ingenuity, has evolved a mechanism to capture these high-quality photons. This mechanism is photosynthesis. In the leaves of every plant and in the cells of countless microbes, tiny molecular machines capture the energy from a sunbeam. They use this ordered, low-entropy energy to perform a chemical miracle. They take simple, disordered, high-entropy molecules from their environment, carbon dioxide from the air and water from the soil, and they build them into complex, highly ordered, low-entropy molecules, like glucose, a simple sugar. This is the creation of order from chaos, the building of a complex structure from simple parts. It is a direct, local victory against the second law of thermodynamics. But this victory comes at a price, and that price is paid back to the universe. The entire system of life on Earth, having captured this high-quality sunlight, then radiates its waste energy back out into space. But it does not radiate it back as high-energy visible light. It radiates it as low-grade, disordered, high-entropy infrared heat. It is a faint, gentle, and chaotic glow, spread out over the entire surface of the planet. This is the perfect transaction. The Earth receives a stream of low-entropy energy from the sun. Life captures it, uses it to build and maintain its own incredible order, and in the process, it degrades that energy, releasing it back into the cosmos as high-entropy heat. The total entropy of the larger system, the sun, the Earth, and the empty space in between has increased, exactly as the second law of thermodynamics demands. The universe has received its payment of chaos. And in exchange, life has been allowed to create its small, temporary, and beautiful island of order. The sun is the ultimate patron of life, the quiet benefactor that funds our exquisite and ongoing rebellion against the inevitable. The sun provided the raw, low-entropy energy, and the open system of Earth provided the loophole in the second law of thermodynamics. But the great rebellion of life needed more than just a power source. It needed a kitchen. It needed a specific, sheltered environment, where the simple, disordered molecules of the primordial soup could be concentrated, energized, and coaxed into forming the first, more complex structures. The transition from a random collection of chemicals to a self-sustaining, ordered system of process known as abiogenesis is perhaps the most profound and mysterious event in our planet's history. Scientists are still searching for the exact location of this first chemical kitchen, the crucible where the spark of life was first ignited. One of the most compelling and beautiful hypotheses takes us to the bottom of the primordial ocean, to a place of profound darkness and immense pressure. Here, on the seafloor, are hydrothermal vents, great fissures in the Earth's crust where superheated, mineral-rich water from the planet's interior gushes out into the cold ocean. Some of these, known as black smokers, are incredibly hot and acidic. But another type, the alkaline hydrothermal vents, like those found in the modern-day Lost City Field in the mid-Atlantic, are considered by many to be a perfect cradle for life. Imagine a towering, porous rock structure, like a natural underwater cathedral, with warm, alkaline water gently seeping through its intricate network of tiny pores. This environment creates a powerful natural battery. The vent water is rich in hydrogen gas and has a different pH than the surrounding acidic, carbon dioxide-rich ocean water. This creates a natural proton gradient, a difference in electrical charge across the thin mineral walls of the pores. This is astonishingly similar to the way our own cells generate energy today. These tiny, mineral-lined pores could have acted as the first cell walls, concentrating the simple organic molecules brought by comets and created by geological processes, and using the natural energy gradient of the vent to power the first tentative steps towards metabolism. Another, gentler hypothesis takes us from the dark abyss to the sunlit surface, to what Charles Darwin once famously imagined as a warm little pond. Picture a small, shallow body of water on a volcanic island, rich in the chemical building blocks of life. This pond would have been subject to constant cycles of evaporation and refilling. During the dry periods, the water would evaporate, leaving behind a highly concentrated chemical soup. This process of concentration would have dramatically increased the chances of the simple molecules bumping into each other and reacting, forming longer, more complex chains, the first simple proteins and nucleic acids. Then, the rains would return, refilling the pond, allowing these new, larger molecules to move around and interact in new ways. This endless, patient cycle of wetting and drying, powered by the sun and the weather, could have been the gentle, rhythmic engine that slowly cooked the primordial soup into the first ingredients of life. A third possibility is a flash of inspiration from the heavens. The early Earth's atmosphere was a place of violent electrical storms. In 1952, the famous Miller-Urey experiment recreated these conditions in a laboratory. They took a mixture of simple gases believed to exist on the primordial Earth: methane, ammonia, hydrogen, and water vapor, and passed a continuous electrical spark through them to simulate lightning. After just 1 week, they found that the water had turned a dark, cloudy brown. When they analyzed it, they discovered it was filled with complex organic molecules, including several of the amino acids that are the fundamental building blocks of proteins. Lightning, in this view, was the spark, the energetic jolt that transformed simple atmospheric gases into the very stuff of life, which then rained down into the oceans below. Whether in the deep, dark vents, the sunlit shallow ponds, or the stormy skies above, the early Earth was a dynamic and creative chemical kitchen. And in one of these kitchens, or perhaps in all of them at once, a molecule of profound and beautiful potential was about to be born. The primordial Earth was a vast chemical kitchen, a chaotic but fertile place, where the simple building blocks of life were being cooked up by the energy of lightning, volcanoes, and the sun. In this warm chemical soup, amino acids, lipids, and simple sugars were beginning to form. But a collection of ordered molecules is not yet life. A pile of bricks, no matter how well made, is not a house. For life to begin its great rebellion against entropy, it needed something more. It needed a plan. It needed information. In all life that we know today, the information, the architectural blueprint for building an organism, is stored in a magnificent molecule called DNA. And the work of building and maintaining the organism is done by another set of magnificent molecules called proteins or enzymes. This presents us with a profound and baffling paradox, a classic chicken and egg problem. DNA holds the instructions, but it cannot do anything on its own. It needs proteins to read the instructions and to build the cellular machinery, but the instructions for building those very proteins are themselves encoded in the DNA. So, which came first? You cannot have proteins without DNA, and you cannot have DNA without proteins. It is a perfect, logical circle, a seemingly impossible barrier to the origin of life. For decades, this puzzle stood as one of the great unanswered questions in biology. But nature, in its quiet and profound elegance, often finds a third way, a solution that is simpler and more beautiful than the problem it solves. And in this case, the solution may lie with a different, more ancient, and more versatile molecule. It is the humble cousin of DNA, a molecule called RNA, or ribonucleic acid. And a theory that places it at the center of life's origin is known as the RNA world hypothesis. RNA is very similar to DNA. It is a long chain made of a sequence of 4 chemical bases, a language for storing information. But it is also different in a few crucial ways. It is typically a single strand, not a double helix, which makes it more flexible and chemically reactive. And for a long time, RNA was seen as a simple messenger, a temporary copy of the DNA's instructions, used to carry the blueprint from the cell's nucleus out to the protein-making factories. But in the 1980s, a Nobel Prize-winning discovery changed everything. Scientists found that some RNA molecules, which they named ribozymes, could act as enzymes. They could fold themselves into complex three-dimensional shapes, just like proteins, and could actively catalyze chemical reactions. This was the answer to the paradox. RNA was the magical two-in-one molecule. It could do both jobs. It could store the information, the blueprint, like DNA. And it could perform the work, the chemical catalysis, like a protein. It was both the architect and the builder, the recipe and the cook. This discovery gave birth to the RNA world hypothesis. It proposes that before the age of DNA and proteins, there was an age of RNA. The first life on Earth was not a cell as we know it, but a simple, self-replicating RNA molecule, floating in the primordial soup. Imagine a single complex RNA strand, formed by chance in a warm little pond or a deep-sea vent. This strand had the unique ability to act as a template, attracting the simple chemical building blocks from the surrounding water and, through its own enzymatic action, stitching them together to form a copy of itself. This was the birth of heredity. This was the birth of information. For the first time, a complex, ordered structure had found a way to preserve its own order and pass it on. The rebellion against entropy now had a memory, and with memory came the engine of evolution, natural selection, now acting at the molecular level. The replication process would not have been perfect. Errors or mutations would occur. Some of these new RNA strands would be less efficient at copying themselves and would fade away. But others, by pure chance, might be slightly better, faster, or more stable. These superior replicators would make more copies of themselves, and soon, the primordial soup would be dominated by the most efficient RNA molecules. The quiet, invisible war for survival had begun, fought not with claws and teeth, but with the subtle chemistry of self-replication. This ancient, forgotten world of RNA was the true dawn of life, the moment that information became the ultimate weapon in the long and beautiful war against the chaos of the universe. The RNA world was a world of beautiful, chaotic creation. In the primordial soup, these versatile molecules were the pioneers, the jacks of all trades, acting as both the blueprint and the builder. They stored the first whispers of genetic information and performed the first simple acts of chemical work. But RNA, for all its ingenuity, had a fundamental weakness. It was a fragile and volatile molecule. Its single-stranded structure made it vulnerable to chemical degradation, and its replication process was prone to errors. It was a brilliant first draft of life, but it was not a story built to last for eons. For life to truly entrench itself, to build the great complex empires of biology, it needed a better way to store its most precious asset, its information. It needed a library, a vault, a sacred text that was stable, reliable, and could be copied with near-perfect fidelity for billions of years. And so, through the slow, patient work of evolution, a new molecule rose to prominence, a molecule that would become the undisputed and immortal king of the genetic world. This was the rise of DNA. The transition from an RNA world to a DNA world was one of the most significant events in the history of life. It was a shift from a chaotic, experimental phase to one of profound stability and permanence. DNA, or deoxyribonucleic acid, is a close cousin of RNA, but with a few subtle chemical modifications that make it vastly superior as an archive for genetic information. The most obvious of these is its magnificent and iconic structure, the double helix. Imagine two long complementary strands, two molecular ribbons, wrapped around each other in a graceful, twisting ladder. This structure is not just beautiful, It is a masterpiece of chemical engineering. The double helix is far more stable and far less reactive than the single, exposed strand of RNA. It protects the precious genetic code on the inside, shielding it from chemical damage and the random thermal noise of the cellular environment. It is the difference between a loose, unbound scroll and a perfectly bound, hardcover book. Furthermore, the very structure of the double helix contains a brilliant and elegant mechanism for its own preservation and replication. Because the two strands are complementary, with the chemical base A on one strand always pairing with T on the other, and C always pairing with G, each strand is a perfect mirror image of the other. This means that if one strand is damaged, the cell can use the other strand as a perfect template to repair the error. It is a self-correcting system, a text with its own built-in backup copy. This structure also allows for replication with an astonishing degree of accuracy. When it is time for a cell to divide, great molecular machines, enzymes like DNA polymerase, move along the DNA strand, unwinding the double helix and using each of the two strands as a template to build a new, complementary partner. This process is not just a simple copy and paste. The DNA polymerase enzyme is a meticulous proofreader. As it builds the new strand, it constantly checks its own work. If it accidentally inserts the wrong chemical letter, it can pause, go back, snip out the mistake, and insert the correct one before moving on. The result is a replication process, with an error rate of less than 1 in a billion. This incredible fidelity is what allows the vast library of an organism's genetic information to be passed down, generation after generation, with almost no corruption. With the rise of DNA, a new and far more efficient division of labor emerged within the cell. DNA became the master archive, the sacred, permanent text kept safe and protected in the cell's nucleus. RNA, the old master, took on its modern, more specialized roles as the temporary messenger, the disposable copy of the blueprint, used for the day-to-day work of building proteins. And the proteins themselves became the specialized, powerful workforce, the true machines of the cell. This elegant separation of duteous storage, messaging, and action allowed for a level of complexity and stability that the old RNA world could never have achieved. Life now had its immortal book, a river of information that could flow, almost unchanged, through the deep river of time, carrying the story of order from one generation to the next. The rise of DNA provided life with its immortal library, a stable and reliable archive for the precious information of order. But a library, no matter how magnificent, is vulnerable if it is left out in the open. The chaotic, chemical ocean of the primordial Earth was a dangerous place for these delicate, self-replicating molecules. They were constantly bombarded by harsh ultraviolet radiation, jostled by random thermal motion, and at the mercy of a turbulent and unpredictable environment. For life to truly establish a foothold, for it to begin building the complex machinery of biology, it needed more than just a blueprint. It needed a home. It needed a sanctuary. It needed a fortress. This is the story of the birth of the cell, the fundamental unit of all life as we know it. And like so many of the great innovations in life's history, it was not the result of a complex, intentional design, but of a simple, elegant, and almost magical act of self-assembly, driven by the basic laws of physics and chemistry. The building blocks of this first fortress were another type of molecule that was abundant in the primordial soup: lipids. Lipids are, in simple terms, fats, and they possess a remarkable and profoundly important property, a kind of split personality that would change the course of life on Earth. A lipid molecule has two distinct ends. It has a head that is hydrophilic, meaning it is attracted to water, and it has a long tail that is hydrophobic, meaning it is repelled by water. Now, imagine what happens when you throw a vast number of these two-faced molecules into the watery environment of the early ocean. They do not just float around randomly. They spontaneously organize themselves in the most energy-efficient way possible, a beautiful act of self-creation. They arrange themselves to hide their water-fearing tails from the surrounding water, while keeping their water-loving heads in contact with it. This self-assembly can result in several structures. Sometimes they form tiny spheres called micelles, with their tails tucked into the center. But more importantly, they can form a structure called a lipid bilayer. Imagine two layers of these molecules, arranged tail to tail, forming a continuous, flexible sheet. On the outside of this sheet, one layer of heads faces the ocean. On the inside, another layer of heads faces a small, trapped pocket of water. And sandwiched between them, protected from the water on both sides, are all the hydrophobic tails. This structure, a double-layered self-sealing membrane, is the foundation of every single cell that has ever existed. The first cells were likely nothing more than these simple vesicles, these tiny, hollow spheres of lipid membrane that by pure chance happened to enclose a few of the self-replicating RNA molecules and the chemical building blocks they needed. But this simple act of enclosure was a revolutionary leap. It was the moment life built its first wall. This membrane created a profound and fundamental division in the universe, an inside and an outside. Inside the fortress of the cell, life could finally begin to control its own environment. It could maintain a stable, internal chemistry, a specific pH, and a specific concentration of salts and minerals, perfectly optimized for the delicate work of replication and metabolism. It was a protected sanctuary, a quiet and ordered workshop, shielded from the chaos and randomness of the external world. The membrane was not an impermeable wall. It was a selective gatekeeper. It could allow the necessary raw materials to enter, while keeping harmful substances out. It was the birth of a border, the birth of individuality. The rebellion against entropy now had a home, a self-contained and self-regulated kingdom, from which it could begin to build the great empires of biology. The first cell had built its fortress, a delicate membrane that separated the precious, ordered world inside from the chemical chaos of the ocean outside. But a fortress, no matter how well built, is just a static structure. To truly be alive, to wage a continuous and active rebellion against the forces of entropy, this new entity needed an engine. It needed a way to power itself, to repair its walls, to copy its sacred texts, and to maintain its fragile island of order. This is the story of the birth of metabolism, the quiet, intricate, and ceaseless engine that drives every living thing. Metabolism is the sum of all the chemical reactions that occur within a living cell, a vast and beautifully choreographed network of molecular transformations. If the cell is a city, then metabolism is its entire infrastructure, its power plants, its factories, its recycling centers, and its transportation networks, all working in perfect, silent harmony. Its primary purpose is to manage energy, to take the ordered, low-entropy energy from the outside world and use it to perform the constant work of staying alive. At the heart of this energy economy is a single, remarkable molecule, the universal energy currency of all life on Earth. Its name is adenosine triphosphate, or ATP. Think of ATP not as a great power plant, but as a tiny, rechargeable battery. When the cell captures energy, for example from breaking down a sugar molecule, it uses that energy to charge these tiny batteries, converting a lower energy molecule, called ADP, into the high-energy ATP. This charged ATP molecule can then travel anywhere in the cell where work needs to be done. When a process requires energy to build a new protein, to repair a damaged piece of DNA, to pump waste out of the cell, ATP molecule arrives, releases its stored energy in a tiny, controlled burst, becoming ADP again, and the work gets done. The cell is constantly charging and discharging trillions of these tiny batteries every single second. It is a system of incredible efficiency and elegance. The great metabolic engine has two main branches, two sides of the same coin. The first is catabolism, the process of breaking things down. This is how the cell acquires its energy. It takes in large, complex, low-entropy molecules from its environment like the glucose created by photosynthesis and, through a long series of carefully controlled chemical reactions, It systematically breaks them down into smaller, simpler, high-entropy molecules. With each broken bond, a small amount of energy is released and captured to charge the ATP batteries. The second branch is anabolism, the process of building things up. This is where the cell uses the energy stored in its ATP batteries to create order. It takes simple raw materials and, following the blueprints stored in its DNA, it stitches them together to build the complex, highly ordered structures it needs to survive. New proteins, new lipids for its membrane, new strands of DNA for replication. This is the constant work of construction and repair, the active, moment-to-moment fight against the second law of thermodynamics. This engine never stops. From the moment a cell is born to the moment it dies, its metabolic pathways are humming with activity. Life is not a static state of being ordered. It is the continuous, energy-consuming process of maintaining order. The moment this engine stops, the moment the flow of energy ceases, the rebellion is over. The cell can no longer repair itself, can no longer maintain its internal balance. And the patient, ever-present force of entropy begins its work, and the beautiful, complex machinery of the cell slowly, inevitably, decays back into the simple, disordered chemical soup from which it once arose. The quiet hum of the engine is the very sound of life itself. For its first 2 billion years, life's rebellion against entropy was a quiet and humble affair. It was a microscopic revolution, fought by single-celled organisms in the warm primordial oceans. They had built their cellular fortresses, perfected their metabolic engines, and faithfully copied their sacred genetic texts. But their world was still a fundamentally alien one. The Earth's atmosphere was a thick, hazy mixture of nitrogen, carbon dioxide, and methane, almost entirely devoid of the free oxygen that we now depend on. Life was anaerobic, meaning it had evolved to thrive in an oxygen-free environment. For these early organisms, oxygen was not the breath of life. It was a deadly, corrosive poison. But then, in a quiet corner of this ancient ocean, a new kind of rebel emerged. A group of microbes known as cyanobacteria developed a revolutionary new trick, a new way to harness the low-entropy energy of the sun. This was oxygenic photosynthesis. It was a process of incredible power and efficiency, allowing these tiny organisms to take the abundant carbon dioxide and water from their environment and, using the energy of sunlight, convert it into sugar for themselves. But this new powerful process had a waste product, and that waste product, released in a constant, gentle stream from these trillions of tiny cells, was oxygen. At first, this new gas did not build up in the atmosphere. The early oceans were rich in dissolved iron, and as the cyanobacteria released their oxygen, it immediately reacted with this iron, causing it to rust. For hundreds of millions of years, this process continued, a slow, planetary-scale chemical reaction. The oceans of the world literally rusted. This great rusting event left behind a spectacular and undeniable piece of geological evidence, a story written in stone that we can still read today. These are the banded iron formations, vast layers of iron oxide or rust, alternating with layers of silica, found in the oldest rocks on Earth. They are the fossilized remains of the Earth's first great pollution crisis, a silent testament to the moment life first began to fundamentally re-engineer the chemistry of its own planet. But eventually, after millions of years, most of the iron in the oceans had been used up. The great rust sink was full. And now, the oxygen, with nowhere else to go, began to escape from the water and build up in the atmosphere. This was the great oxidation event, and it was a catastrophe for the incumbent anaerobic life on Earth. To these organisms, this new oxygen-rich air was a poison that destroyed their cells and broke down their metabolic pathways. It triggered one of the first and greatest mass extinctions in our planet's history, a silent genocide that wiped out the majority of the world's dominant life forms. But from the ashes of this catastrophe, a new world was born. The presence of free oxygen in the atmosphere allowed for the evolution of two crucial innovations. First, It created the ozone layer, a protective shield in the upper atmosphere that blocked the sun's harshest ultraviolet radiation, making the surface of the land safe for life to eventually colonize. Second, it allowed for the evolution of a new and far more powerful form of metabolism, aerobic respiration, the very process that your own cells are using right now. This process, which uses oxygen to break down food, is nearly 20 times more efficient than anaerobic metabolism. It was this new, high-energy lifestyle that would eventually power the evolution of all complex, multicellular life, from the first simple animals to the intricate workings of the human brain. Life had not just survived. It had terraformed its own planet, transforming a hostile, alien world into one that was perfectly suited for a new and more complex chapter in its long rebellion. As life's rebellion against entropy grew more ambitious, as it moved from the simple solitude of a single cell to the vast, cooperative metropolis of a multicellular organism, it encountered a new and profound paradox. To build a higher level of order, a more complex and magnificent structure like a plant or an animal, it had to invent a new and powerful tool. And that tool, ironically, was death. In the early days of the RNA world and the first simple cells, life was, in a sense, immortal. A single-celled organism does not grow old and die in the way we do. It simply grows to a certain size, copies its genetic material, and divides into two identical daughter cells. The original cell does not cease to exist. It simply becomes two. This process of binary fission is a kind of perpetual generational immortality, a continuous chain of replication stretching back to the very dawn of life. But for a complex, multicellular organism to exist, this selfish immortality of the individual cell had to be sacrificed for the greater good of the whole. Imagine building a great and intricate sculpture out of living clay. For the final sculpture to have a beautiful and functional shape, some pieces of the clay must be carefully carved away. This is precisely what happens during the development of a complex organism. This process of controlled, programmed cell death is called apoptosis. It is a beautiful and elegant biological process, a quiet and orderly self-destruction. When a cell receives the signal to undergo apoptosis, it does not simply burst and spill its contents, which would cause inflammation and damage to its neighbors. Instead, it begins a meticulous process of self-dismantling. Its DNA is neatly fragmented, its internal machinery is broken down, and its entire structure shrinks and breaks apart into small, membrane-bound packages, which are then tidally consumed and recycled by neighboring cells. It is a death of quiet dignity, a final, selfless act. We can see this process at work in our own bodies before we are even born. The hand of a developing human embryo begins as a solid, paddle-like structure. The individual fingers are formed only when the cells in the webbing between them receive the genetic signal to undergo apoptosis, carving out the empty spaces that give our hands their shape and dexterity. Apoptosis is the sculptor of life, the artist that uses death to create form. It is also the vigilant guardian of our health. Every day, cells in our body can become damaged or develop cancerous mutations. Apoptosis is the primary mechanism that identifies these faulty cells and instructs them to self-destruct before they can cause harm to the larger organism. On the grander scale of evolution, the death of the individual organism also became a powerful and necessary strategy. A world filled with immortal creatures would be a world of stagnation. There would be no room for new generations, no space for new adaptations to emerge. The death of the individual clears the way for the young, allowing the great slow engine of natural selection to continue its work. It allows new genetic combinations and mutations to be tested against the challenges of a changing environment. In this sense, death is not the enemy of life. It is the engine of evolution. It is the price that complex life had to pay for the ability to adapt, to change, and to become ever more intricate and beautiful. It is the ultimate act of letting go, the sacrifice that allows the great, immortal river of DNA to continue its journey, flowing through the temporary vessels of our own finite lives. Life's quiet rebellion against entropy has, until now, been a story of internal triumphs. We have seen it build the fortress of the cell, invent the immortal library of DNA, and even learn to wield the tool of death to achieve a higher, more complex order. We have even witnessed its power to terraform the world, transforming a poisonous, alien atmosphere into the oxygen-rich air we breathe today. But the ambition of life, its relentless drive to create and sustain order, may be even grander than that. Our investigation now zooms out to its widest possible lens, to entertain a beautiful, controversial, and profoundly comforting idea that life does not just exist on the planet. It may, in a very real sense, be the planet. This is the heart of the Gaia hypothesis, a theory first proposed in the 1970s by the scientist James Lovelock and the microbiologist Lynn Margulis. Named after Gaia, the ancient Greek goddess who was the personification of the Earth itself, the theory proposes that the entire biosphere of our planet, every tree, every microbe, every fish in the sea, and every bird in the sky acts collectively as a single, vast, self-regulating superorganism. In this view, the Earth is not just a rock that happens to have life on it. The Earth is, in a functional sense, alive. The Gaia hypothesis suggests that the biosphere actively maintains and regulates the conditions on the planet's surface to keep them optimal for life. It is not a conscious or intentional process, but an emergent property of the countless interconnected feedback loops between living things and their non-living environment. Life, in this view, is not just a passenger on spaceship Earth. It is the ship's life support system, constantly fine-tuning the temperature, the atmospheric composition, and the ocean chemistry. Consider the composition of our atmosphere. It is a strange and highly unstable mixture of gases, primarily nitrogen and oxygen. That 21% oxygen level is a chemical knife edge. If it were to rise to just 25%, the air would be so flammable that even damp vegetation could ignite from a single lightning strike, leading to catastrophic global wildfires. If it were to drop much lower, complex, air-breathing animals like us could not survive, and yet, for hundreds of millions of years, this level has remained remarkably stable. The Gaia hypothesis argues this is not a coincidence. It is the result of the biosphere actively regulating the production and consumption of oxygen, a planetary scale balancing act. Or, consider the temperature of the Earth. Our Sun, like all stars, has grown progressively brighter over its long life. Billions of years ago, it was significantly fainter and cooler. By all rights, the early Earth should have been a frozen ice ball, and yet the geological record shows that it had liquid oceans and was warm enough for life to begin. This is the faint young sun paradox. The Gaian explanation is that early life, particularly methane-producing microbes, created a powerful greenhouse effect that kept the planet warm. Then, as the sun grew hotter over eons, new forms of life, like photosynthetic organisms, evolved and began to draw down carbon dioxide, another greenhouse gas, effectively cooling the planet and preventing it from overheating. Life, in this view, has acted as a planetary thermostat, adjusting the atmosphere to compensate for the changing output of our star. While the idea of Earth as a single living organism is a powerful metaphor, modern science has refined this concept into a more rigorous field known as Earth system science. This field studies the planet as a single, integrated system of complex feedback loops between the biosphere, life, the atmosphere, air, the hydrosphere, water, and the geosphere, rock. It confirms Lovelock's central intuition that life is not a passive player, but an active force that fundamentally shapes its own environment. The quiet rebellion against entropy, it turns out, is not just a personal struggle. It is a planetary-scale, cooperative project, a 4-billion-year-old endeavor by life to build and maintain its own beautiful, ordered, and improbable home in a universe that otherwise tends towards chaos. And so, we have seen life's rebellion against entropy unfold on a planetary scale, a 4-billion-year project to build and maintain a world of beautiful, complex order. From the first self-replicating molecule, to the fortress of the cell, to the great self-regulating system of the global biosphere, life has relentlessly pushed back against the tide of chaos. But this grand story of increasing order and complexity leads us to a final and perhaps most profound chapter. It leads us to the most intricate, most ordered, and most mysterious structure that we know of in the entire universe. It leads us to the human brain. If life is a rebellion, then the conscious mind is its masterpiece, the pinnacle of its achievement. Consider for a moment the sheer, staggering complexity of the organ that is right now processing these words. Your brain contains nearly 100 billion neurons, the same number of stars as there are in our Milky Way galaxy. And each of these neurons is connected to thousands of others, forming a network of an estimated 100 trillion synapses. This is a number so vast, it is difficult to comprehend. There are more connections in a single human brain than there are stars in 1,000 galaxies. This is not just a structure of low entropy. It is a universe of order, a living cathedral of complexity, all contained within the quiet darkness of your own skull. But the brain's rebellion is not just in its physical structure. Its true genius lies in what it does. It is a machine that creates abstract order from the chaos of the world. Every second of your waking life, your senses are bombarded with a torrent of raw, disordered data. Photons of light striking your retina, pressure waves vibrating your eardrum, chemical molecules landing on your tongue. From this chaotic storm of sensory input, your brain does something miraculous. It finds patterns. It constructs a stable, coherent, and meaningful reality. It takes the chaotic flicker of light and shadow and transforms it into the face of a loved one. It takes a random jumble of sound waves and hears a beautiful piece of music. It is the ultimate artist, the ultimate storyteller, constantly weaving the raw, messy threads of sensory data into the rich, ordered tapestry of your subjective experience. And from this ordered perception, something even more extraordinary emerges: consciousness. This is the great, final mystery. We do not yet know how the intricate, electrochemical firing of 100 billion neurons gives rise to the simple, undeniable feeling of being you. But we know that it does. Consciousness is the state in which the universe, through us, becomes aware of itself. It is the pinnacle of life's rebellion against entropy, because it does not just create physical order, it creates the awareness of order. It is the part of the universe that can look back at the stars and understand that it is made of them. It is the part of the story that can recognize that it is a story. Is this, then, the ultimate purpose of life's long, slow climb against the current of chaos? To create a structure so complex, so ordered, that it could finally wake up and appreciate the beauty of the struggle itself? We do not know. But as you lie here, on the edge of sleep, in the quiet sanctuary of your own mind, consider this: you are the current, living embodiment of a 4-billion-year-old rebellion. You are the highest wave of order that this corner of the universe has yet produced. A thinking, feeling, dreaming piece of the cosmos, capable of contemplating the very laws that say you should not exist. And in that quiet, beautiful paradox, there is a profound and gentle peace. We have reached the pinnacle of our story, the emergence of the conscious mind, a structure of such profound and intricate order that it can look back upon the universe and begin to understand its own unlikely origins. It is a breathtaking summit, a testament to a 4-billion-year rebellion against the forces of chaos. And yet, from this high peak of complexity, we must now confront a final, gentle, and perhaps most beautiful truth. All of this intricate dance of life, this magnificent island of order, is exquisitely and profoundly fragile. It is not built to last forever. Life's existence is not a static state. It is a process, a constant, energetic performance. To understand this, let us use a final, quiet analogy. Imagine a river flowing steadily over a submerged rock. In the current just behind the rock, a stable, standing wave may form. It is a beautiful, ordered pattern that holds its shape. a persistent ripple in the flow. It has a clear form, a beginning, a middle, and an end. You can point to it and say, "There is the wave." But what is that wave actually made of? The water molecules that form the wave at this very second are not the same molecules that formed it a second ago, and they will not be the same ones that form it a second from now. The matter is in constant flux, a ceaseless river of H2O molecules flowing through the pattern. The wave is not a thing. It is a stable form through which matter and energy are constantly passing. Life is this standing wave. You are this standing wave. The atoms that make up your body are not permanent. The carbon atom in a cell in your hand today may have been part of a leaf a year ago. The water molecules in your blood are constantly being replaced. Over the course of several years, nearly every atom in your body is exchanged for a new one. You are not the same physical stuff that you were as a child. The matter has been replaced over and over again. So what then is the you that persists? It is the pattern. It is the information, the blueprint stored in your DNA, and the intricate, ever-changing network of connections in your brain. It is the process of metabolism, the continuous flow of energy that maintains that pattern against the relentless current of entropy. Your existence is not a solid, unchanging statue. It is a gentle, persistent flame. The flame has a shape, a form, a reality, but the fuel and the air that create it are in constant flux. This fragility is not a flaw in the design of life. It is the very essence of it. Life exists in a state of dynamic equilibrium, a delicate and continuous dance between building up and breaking down, between order and the ever-present pull of chaos. It is a temporary victory, a brief and beautiful moment of defiance. A crystal is ordered and can last for millions of years, but it is dead. A flame is fragile and fleeting, but it is alive. Its beauty lies not in its permanence, but in its performance. And it is this very fragility, this knowledge that our time as an ordered pattern is finite, that gives our existence its profound and precious meaning. And so, our long and quiet journey through the great paradox of existence comes to its final, gentle close. We began with a simple, unshakable law of the universe, the relentless march of entropy, the principle that all things must inevitably move from a state of order to one of chaos. We journeyed to the far distant future to witness the ultimate fate of the cosmos, the cold and silent equilibrium of the heat death, the final victory of this law. And then we traveled back to a young, chaotic, and fiery Earth, a world that seemed a perfect embodiment of this principle, a place where the formation of complex order seemed an impossibility. Yet, from that chaotic cradle, a rebellion began. We have seen how life, this beautiful and improbable phenomenon, found a clever loophole in the universe's most fundamental rule. It learned to be an open system, a vortex of order, powered by the low-entropy gift of the sun. We have traced its story, from the first self-replicating molecule, to the immortal library of DNA, to the protective fortress of the cell. We have witnessed it invent the intricate engine of metabolism, the selfless act of programmed death, and even learned to terraform its own planet, transforming a hostile world into a vibrant, oxygen-rich home. We have seen it build structures of ever-increasing complexity, culminating in the most ordered object we know, the conscious human brain. Life does not violate the laws of the universe. It is a local and exquisitely temporary phenomenon. It is a small island of decreasing entropy in a vast, cosmic ocean of increasing entropy. We are like small, beautiful flames, burning brightly for a short time in an immense and darkening room. The flame is a structure of incredible order, a dance of light and heat. But it can only exist by consuming an ordered fuel, source the wax of the candle and, releasing its energy back into the room, as disordered, high-entropy heat and light. The flame creates a local pocket of brilliant order, but in doing so, it speeds up the overall increase of chaos in the room around it. Our existence is not a mistake. It is an extraordinary and beautiful exception, a brief and glorious defiance of the universe's default state. And it is this very fragility, this knowledge that our time as an ordered pattern is finite, that gives our existence its profound and precious meaning. The constant, quiet struggle to maintain our order, to build, to learn, to love, to create, that is the very definition of being alive. The beauty of the flame is not in its permanence, but in the light it casts while it burns. And now, as you prepare to drift into sleep, you are participating in this great and ancient cycle. Sleep is not an absence of life. It is a vital part of its process. It is the quiet, nightly work of restoration, a time when your body and mind meticulously repair the day's wear and tear, rebuild their ordered structures, and recharge their energy, all in preparation for another day of the beautiful rebellion against chaos. You are tending to your own gentle flame. So let go of the day, trust in this deep restorative process, and find peace in the knowledge that you are a temporary, beautiful, and profoundly improbable flame of order, burning brightly in the quiet, endless night of the universe. Sleep well,